Hey everybody, Mr. Murphy here with another video lesson for you. Today's is about chords of circles and how they relate to diameters and radiuses. Specifically, we're going to go over one theorem here about them, which is that if I have a diameter or radius that is perpendicular to a chord, then that diameter or radius bisects the chord. Remember that bisects means cut equally in half. So I'm going to put cut into equal halves. So in other words, if a diameter or radius is perpendicular to a chord, it goes right through the middle of that chord, cuts it into two equal halves. On this picture, our chord is line segment AB. That's the chord. And then the diameter that is perpendicular to it, right here, is line segment CD. Because they make a right angle, the two halves of line segment AB are the same length. So notice, because this is a diameter, it also contains a radius. PC is a radius, and since PC is perpendicular to AB, that also works to split it in half. So this could work with a diameter or a radius. Okay, we might also make use of the converse of this theorem, which is just that if you have a diameter or radius and you happen to notice that it bisects the chord, you can determine that they're perpendicular. Cool. Now, why is it important for us to notice these right angles and to notice these bisected chords? Well, if you have two line segments that form a right angle, you can often find this length by doing a squared plus b squared equals c squared. So that is what this theorem about chords and diameters can lead us to. It lets us find a way to use Pythagorean Theorem to solve for measurements of circles, like chords or radiuses. Okay, so we're going to take that theorem and use it to help us on example 1. We're going to solve for x. So x that we're solving for is going to be this segment right here. I'm going to highlight it nice and bold. Right there. That's what we're trying to find the length of. And I noticed this right angle here, which means that I have a radius from here to here, and that radius is perpendicular to a chord. I also noticed that for the chord, half of its length, or rather, the length of one segment of the chord is 18.4. Now, according to our theorem, if a diameter bisects or a radius, is perpendicular to a chord, if we notice that right angle, then it bisects that chord. So if this part is 18.4, this part is too. Cool. So that's going to help us out. I also notice that I have the measurement for the diameter here. Here, let's do this. The diameter is 43.4 units. And if we know that, we know that the length of this radius from here all the way to the center is just going to be half of that. So if I look at 43.4 and I split it in half, 43.4 over 2, that will tell me the length of my radius. So that comes out to 21.7. 21.7. That's the length of your radius. Cool. So that tells me this length here is 21.7. But more importantly, this length here is 21.7. And now if you'll notice, we have two sides of this little right triangle that we see in the picture here. So I'm going to kind of draw that triangle out separately. Right angle is right here. We don't know this side, but we know the radius here is 21.7, and we know this side is 18.4, because that's half of the chord. So we need to find this missing length so that we can solve for x, because together they also make a radius, and they should also be 21.7. Let's go ahead and find this missing part, though. So I see that this is the hypotenuse of my triangle. So let's make this a and b. So a squared plus 18.4 squared equals 21.7 squared. I'm going to go ahead and find both of those numbers. We're not going to round anything yet, but we will round our final answer to the nearest tenth more than likely. Okay, so 18.4 squared is 338.56. 21.7 squared, let's do that next. That gives me 470.89. Then we subtract this one from both sides. That cancels. I'm going to move this up a little. Then I get a squared equals 132.33. Alright, so last but not least, to find that missing length, I got to take the square root of this number, like so. And when I do that, that comes out to, now we're going to go ahead and round, that's going to come out to about 11.5 units. So this length from here to here is worth 11.5 units. Okay. Cool. So that's still not our answer, right? We wanted to solve for x. But if you notice, the length we just found by doing Pythagorean Theorem plus x amounts to a radius. And what do we know about the radius? Radius has a length of 21.7. So I'm going to set it up like this. X plus 11.5 equals 21.7. And then I'm just going to subtract minus 11.5, minus 11.5, cancel. And then my final answer I'm left with should be x equals 10.2. Okay. Alrighty. So I wanted to start with that example, mainly because it shows you everything that you might be asked to do with a theorem like this. We started with the diameter, we split it in half to get the radius. That told us this length, and that even helped us when we were solving for x at the end, because we had to use the radius. We also saw that chord split in half, so we had to know to take this 18.4 and know that this line segment has the same length. So put another 18.4 right here. Cool. So I'm going to show you example number 2 now. This one is a little bit simpler, but we're going to have to do some drawing ourselves. It says a chord of a circular clock is 12 inches long, and its midpoint is 8 inches from the center of the circle. What is the length of the radius of the clock? So R equals question mark. Okay. Alright, so first things first, we are going to draw the chord. It says the chord of the circular clock is 12 inches long. Now remember, chords are just any line segment where the endpoints lie on the circle, like that. I'm going to label that A and B. So the chord will be line segment AB. There we go. And now the next thing that the problem says is that the midpoint of this chord is 8 inches from the center of the circle. So first I'm going to mark the midpoint of my chord. Doesn't be exact, but if this is the midpoint, we know that this segment and this segment have the same length. Now we're trying to find the length of the radius. So I'm going to go ahead and draw a radius right here. Alright, now we know that this midpoint is 8 inches from the center of the circle. So right here, I can go ahead and label it 8 inches. Cool. Now I also want to label the other measurements I have, which is the chord. I know the chord is 12 inches long, and this is the midpoint. So if I'm thinking midpoint, that splits it in half, right? So half of 12 would be 6 inches and 6 inches. Okay. Alright, so we want to know what is the radius of the clock. And we have a part of it. This part here is 8 inches. We're missing, however, this little part. And we're not entirely sure how we might get that yet. I know that since this is split in half, the chord and the radius make a right angle. That's part of our theorem. Now, these two sides make a right angle, so naturally, why not take these 2 points and connect them? Because when we do, look at that nice triangle shape that we get. So, with this triangle, oh, there we go. We've got a 6-inch side, 8-inch side, and then this side is the radius. This is another radius of the circle, which means it should be the same length as this radius. Cool. So now let's go ahead and set that up. Draw my triangle a little bit bigger. Not a right triangle, I know, but bear with me. Okay, so this side is 6 inches. This side is 8 inches. Obviously not to scale, but that's how we have it in the drawing, so I'm going to go ahead and continue. This is the radius. And once again, we're going to set up a squared plus b squared equals c squared. In this case, the hypotenuse would be the radius, so r squared. And then over here we have 6 squared plus 8 squared. Okay, that's going to give us 36 plus 64. Those two numbers add to 100. And last but not least, take the square root of both sides so that you can get r. The square root of r squared is just r, the radius, and then square root of 100 is 10. So the radius would be equal to 10 inches. Cool. Alright, awesome. So when you are doing your problems involving chords and diameters, as soon as you see that you have a chord, like that, or like the chord on the clock, and as soon as you see a right angle, or you see the chord is split in half, it's pretty much Pythagorean Theorem time. So just look out for those places where you might be able to do that. Alright, I hope this lesson was helpful for you guys. Make sure you kind of are following along with it, doing the examples out at the very least, and then that should help you with assignment 4, which is going to be posted a little bit later today. Got another video coming for you guys on that one. Alright, bye-bye.